Hi everyone, this is Kyle and Olivia, and we're here to show you our project about the optimization of a train wheel using ANSYS. We'll start with some background information. Trains have been used across the world since the 1800s. Early trains usually failed from fatigue, even though they were designed with high factors of safety due to yielding. We used ANSYS to analyze and optimize a large train wheel. We also were able to use ANSYS fatigue tool to calculate the factor of safety and life. Our original design was made using steel, and a rough cross-section was drawn using ANSYS. It was rotated around the axis to form the wheel. After the original analysis was done, the cross-section was modified to reduce the weight and amount of material used. Here is shown our original inspiration for our cross-section. The total diameter is about 1 meter long, and at its thickest portion, the cross-section is 0.13 meters. The diameter of the axle is about 0.2 meters for our original design. Here are the analysis conditions we used for all three designs. We used a fine mesh with tetrahedron elements. We put a fixed support where the axle would be and a 50,000 Newton meter moment around the flange that rolls on the train track. We used ANSYS to calculate the equivalent stress, deformation, and safety factor of the wheel. Here is shown where the moment was applied on each of our wheels.
The original design results are displayed below. You can see that the max stress of 13.78 megapascals is located along the edge of the hub. You can also see that the minimum safety factor is 6.3 in the same location. Given the high safety factor, we decided we could make changes to the geometry to minimize weight while still staying within a significant safety factor. For the first design iteration, we decided to change the fillet radius from 20 millimeters to 5 millimeters. We knew this would increase stress at this location, but given the significant safety factor, we thought removing this material would still be within limits. Changing the fillet radius doubled the maximum stress to 26.45 megapascals. The safety factor due to fatigue was reduced to 3.3. We decided that we could take out more material in the next design iteration, while still remaining within spec. For our final design iteration, we decided to change the thickness of the middle portion of the wheel. At its thickest point, we changed it from 31.5 millimeters to 20 millimeters in order to save weight. The final design iteration cut out much more weight than the first. However, the maximum stress was barely increased, and the safety factor was not decreased at all.
Here is the conclusion of our results. Decreasing the fillet radius from the first design increased the max stress, reduced the factor of safety, but still resulted in infinite life. Decreasing the width of the intersection had little effect on our maximum stress, almost no effect on the factor of safety, and reduced our weight by 14 kilograms or about 30 pounds. While we also originally looked at deformation of the wheels, it was pretty much negligible for all of our designs, so decided to focus on other elements instead. Future improvements for our optimization would be to make more severe modifications to the geometry. We could also use a topology software to optimize the wheel in more complicated ways than doing it ourselves. Thank you for watching our presentation. Are there any questions?